Are you a student, a teacher, or simply an internet user? Now, then I guess we can both agree that getting the best information on the internet could be a tedious work. Now, what if I told you that there is a shortcut to get this information? Stay tuned and I'll show you how to achieve this.
All you have to do is open your browser and search for ChatGPT, or simply type in chat.openai.com. It will ask you to sign up and just pop in your details and you're good to go. Now all you have to do is type in the things that you want ChatGPT to give you the information to. For this video, I would like to learn more about the golden ratio. So I'll type in history of the golden ratio. And voila! ChatGPT will give you a concise and structured answer. Next, I would like to learn the mathematics behind the golden ratio. Say, for example, I am not satisfied with the answers given, I can simply click Regenerate Response, and ChatGPT will come up with other answers. Note that ChatGPT simply browses the internet for you and choose the information to be shared with you. Therefore, it is at times still important to know the sources to these answers. We can simply ask ChatGPT to provide us the sources as follows. Now that we have the basic to ChatGPT, let's summarize the answers given from ChatGPT in the video I created on golden ratio. Enjoy! Suppose I ask you, for example, what do the petal arrangement in a red rose, the famous painting Sacrament of the Last Supper, and the spiral shells of mollusks all have in common? Hard to believe, but these very examples do have in common a certain number of geometrical proportion known since antiquity and now represented by a Greek letter phi. This proportion is the ratio of a line segment cut into two pieces of different lengths, such that if A is the longer segment and B is the shorter segment, it can be written as A plus B over A equals to A over B. This number in the 19th century was given the honorifics golden number, golden ratio, and golden section. A book published in Italy at the beginning of the 16th century went so far as to call this ratio the divine proportion. Represented in shorthand by the decimal 1.618, phi is an irrational number followed by an infinite number of digits and is accurate enough for almost any practical purpose we ask it to serve. Throughout history, the ratio for length to width of the rectangles of phi has been considered the most pleasing to the eye. First clear definition of what has later become known as the golden ratio was given around 300 BC by the founder of geometry as a formalized deductive system, Euclid of Alexandria. History records that ancient Greek mathematician Euclid, as describing it first in Book 6 of his Mathematics treatise Elements,
a straight line is said to have been cut in extreme and mean ratio 1 as the whole line is to the greater segment, so is the greater to the less.
Comprised of 13 books, Euclid's Elements contains illustrated definitions, postulates, propositions, and proofs covering geometry, number theory, proportions, and incommensurable lines, which are those that cannot be expressed as a ratio of integers. Although the proportion known as the golden ratio has always existed in mathematics, geometry, and nature, exactly when it was first discovered and applied with by mankind is unknown. It is reasonable to assume that it has been discovered and rediscovered throughout history. The earliest references to what we now know as the golden ratio may have come from the time of Pythagoras, a mathematician and philosopher who lived from about 570 BCE to 495 BCE. It is thought that the five-pointed star or pentagram was the symbol of his school, and that he and his followers were the first to discover some of the unique properties of the golden ratio. In the pentagram, the length of every line segment is in a golden ratio relationship to every other one. The mathematical work of the Greeks was kept alive in 9th century Baghdad. Many incredible advances in science and mathematics were made during the ensuing Islamic Golden Age, which lasted until the 13th century. The work of the scholar Muhammad ibn Musa al-Khawarizmi, particularly his discussion of Hindu-Arabic numerals, caught the attention of a young Italian boy during a visit to an Algerian port city with his father, a wealthy merchant from Pisa. The boy, Leonardo Fibonacci, would later become one of the history's most famous mathematicians after the publication in 1202 of his book Liber Abaci. In his book, Fibonacci also wrote a simple numerical sequence based on a theoretical problem of growth in a population of rabbits. That sequence, the foundation for an incredible mathematical relationship behind phi, was known as early as the 6th century by Indian mathematicians, but it was Fibonacci who popularized it in the West. Fibonacci sequence can be explained using the following example. Suppose we have a newly born pair of rabbits, one male and one female. Suppose rabbits are able to mate at the age of 1 month, so at the end of each second month, a female can produce another pair of rabbits. Suppose our rabbits never die and that the female always produces one new pair of one male and one female every month from the second month onward. The question Fibonacci posed was, how many pairs will there be in 1 year? The answer is 144, which is found as the 12th number in this sequence, corresponding to the 12th month of newborn rabbits. Starting with 0 and 1, each new number in the sequence is simply the sum of the two before it, so on, resulting in the following sequence named after Fibonacci. 0, 1, 1, 2, 3, 5, 8, and so on. You can estimate the nth number in the Fibonacci sequence using phi and square root 5 with the equation fn equals to phi to the power of n over square root 5. For example, the 12th number of the Fibonacci sequence can be calculated, thus phi to the power of 12 over square root 5 is equals to 144.0014, which rounds to 144. In the Fibonacci sequence, the ratio of each successive pair of numbers converges on phi. This can also be written as the formula fn plus 1 over fn. To visualize this phenomenon, note that each successive value of the ratio gets closer and closer to phi. At the 40th number in the sequence, the resulting ratio matches phi to 15 decimal places, that is 1.618033988749895. For your information, phi has many unique mathematical properties. Phi is the only number whose square is 1 more than itself, that is, phi plus 1 is equals to phi squared. And it is the only number whose reciprocal is 1 less than itself, that is, 1 over phi is equals to phi minus 1. To show this numerically, imagine if I asked you to divide a line, you could do so in many places. If you cut it in half, you could read this. The whole line is 1. The first segment is 1 over 2, let's call it A. The second segment is also 1 over 2, let's call it B. Now let's cut that line again, and this time think of a different point to cut. Say let A be 2 over 3 of the whole line, you will get the whole line is still 1, the longer segment A is now 2 over 3 and the shorter segment B is now 1 over 3. As we cut the line in different places, we get a variety of differing ratios A plus B to A, and they never matches the ratio for A to B, except when we cut it in that one unique place that Euclid marveled over more than 2,000 years ago. At that single point of equilibrium, we find that the ratio of A plus B to A is 1.618 to 1, and the ratio of A to B is also 1.618 to 1. This is the golden proportion. To determine the numerical value of the golden ratio A over B, we let the length of the longer segment be x units and the length of the shorter segment be 1 unit. This gives rise to the equation x plus 1 over x equals to x over 1. This may be rearranged to form the quadratic equation x squared minus x minus 1 equals to 0. By using the quadratic formula, we get the positive solution to be x equals to 1 plus square root of 5 over 2, that is the golden ratio, and the negative solution to be 1 minus square root of 5 over 2, the negative reciprocal of the golden ratio. There are many applications of golden ratio that we can observe. In art and design, it has been used widely in art since the Renaissance. A famous example of the application of the golden ratio is Mona Lisa. However, application of the divine proportion to this painting is also the most subject to interpretation and debate. In 1955, Dali painted the Sacrament of the Last Supper. This great work contains the golden ratio in two ways. The proportions of the painting correspond directly to the golden ratio. It also features a huge dodecahedron harmoniously dominating the background of the scene. In architecture, almost all the buildings of ancient Greece used this proportion to define the proportion of the height of the buildings to their base. Same has also been used in determining various architectural elements found in the Acropolis of Athens. The Parthenon is one of the most famous examples of ancient Greek buildings designed using the golden ratio. Le Corbusier had been one of the most important architects of modern-style architecture. He drew great inspiration from the golden ratio. Corbusier took extensive use of the Vitruvian Man by Vinci. He also incorporated the proportions of the human body to improve the functionality of his architectural designs. This is the Notre Dame du Haut. In information technology, the golden ratio is often used to guide website, user interface UI, and user experience UX design. Natural balance is a concept where design is grandfathered into basic design principles. In addition to the mathematic ratio, the golden ratio stems from the roots and proportions of nature. The golden ratio has a positive influence on visual perception and is the main reason why many graphics and UI designers apply it to their workflow. In modern mathematics, the golden ratio occurs in the description of fractals, figures that exhibit self-similarity and play an important role in the study of chaos and dynamical systems.